Hello everybody, my name is Benedikt and this is my colleague István Módos.
Hi.
It's our pleasure to present our research about production scheduling with variable energy pricing and power saving states, which we did with Mr. Zdeněk Hanzálek here at the Czech Technical University in Prague.
Our research is motivated by the following two trends that appear in the energy-aware scheduling literature. The first one is the variable energy pricing, where the energy consumption cost changes during the day. An illustration is shown on this figure, where you can see the hour-by-hour evolution of the energy prices in the Czech Republic between the 1st and the 3rd September of 2019. As you can see, the energy prices are not constant and may vary on hourly basis due to negotiations on the electricity market.
The second trend is consideration of power-saving states of production machines. A machine may operate in different states, each having a different power consumption. Throughout the scheduling horizon, the machine may switch between the individual states. However, each transition takes some time and may consume a significant amount of energy. For example, a heating of an industrial furnace from the ambient temperature to the operating temperature of 960 degrees Celsius takes dozens of minutes while consuming hundreds of kilowatts. The states and transition parameters can be captured by a state diagram, a very basic example of which is shown on the slide.
In this work, we consider these two trends together. The goal is to schedule the jobs on the machine such that the power-demanding operations are scheduled within the cheap intervals and the total energy consumption cost incurred by the machine state is minimized. For example, here you can see an optimal schedule to the following simple instance with 3 jobs and 16 intervals, where during the expensive intervals the machine is either off or idle.
Now, let's look at the problem statement more formally. We are given a set of equivalent intervals that partition the scheduling horizon. Each interval is characterized by a cost Ci.
We assume a single machine environment where the machine is operating in one of possible states in every time instant. The set of states consists of a single processing state called proc and at least one non-processing state such as standby, idle, off, and so on. The transition between two states takes some time, which is captured by a function t, and which is measured by a number of intervals. Moreover, the transition has power consumption given by function p.
Finally, we are given a set of production jobs j that need to be processed within the scheduling horizon. Each job is characterized by its processing time p given in the number of intervals. The scheduling is non-preemptive and at most one job can be processed by the machine at a time. All the jobs must be processed while the machine is operating in the processing state.
The objective of the scheduling problem is to minimize the total energy consumption cost during the whole scheduling horizon. The objective is computed from the cost of the states in which the machine operates and the transitions between them.
The solution consists of the job start times as well as the transition behavior of the machine. The scheduling problem presented on the last two slides is denoted by one toState tag in the standard 3-field notation.
Having defined the problem, now we summarize the related literature. The scheduling problem, jointly considering the variable energy prices and machine state, was introduced in 2014 and was further addressed in the literature later on. It was shown that if the order of the jobs is fixed, the problem can be solved in polynomial number of steps. However, if the order is not given, the problem is NPR by reduction from the 3-partition problem. Previously, integer linear programming models of the problem were proposed and tested on relatively small instances with up to 35 jobs and 200 intervals. However, real-world instances may require hundreds or thousands of the intervals so that the jobs can be scheduled with minutes precision. A meta-heuristic was proposed to tackle such large instances. Although this method has a practical relevance, it does not guarantee any bound on the quality of the solutions.
Now, let's look how we solve the problem. Contrary to the previous approaches that model the machine states and transitions explicitly, we decompose the problem into two phases.
The first phase pre-processes the instance by solving an optimal switching problem for every pair of intervals. Solving this switching problem gives us the optimal cost of machine transitions between two intervals. As we shown in the paper, the problem can be solved in polynomial number of steps by our algorithm called spaces.
The second phase is integration of the pre-computed costs of the optimal switchings into specialized ILP and CP models, which are solved by off-the-shelf solvers.
The efficiency of our approach lies in the pruning of the solution space. By pre-computing the optimal switchings and their direct integration into the models, we eliminate the suboptimal switchings which are part of the solution space explored by the explicit models. The important property of the decomposition is preservation of the optimality with respect to the original scheduling problem.
The idea of the preprocessing is illustrated on this slide. We take the transition graph of the machine and we unfold it in a time over all intervals. Now, we compute the shortest path between the processing states in this unfolded graph. This gives us the optimal switching cost between all possible start times of the two consecutive jobs. Once we compute these costs, we can integrate them into the models.
As for the ILP, the integration is quite straightforward. For each possible space between two consecutive jobs, there is a single binary variable indicating whether the space is present in the schedule or not. Then, the objective aggregates the cost of all possible spaces and the job's placements.
Constraint programming provides a specialized scheduling and modeling constructs. Given a sequence of jobs, we can extract the cost of the spaces between the two consecutive jobs using element expression.
Now that we have the optimal switching costs as well as the models, let's look at the experimental results.
Since the CP formalism provides many constructs, it's usually possible to build a model for one problem in many ways. However, it's not often straightforward to see which model performs the best. Therefore, we experimented with many different implementations, which have varying performance, as can be seen in the figure showing the aggregated optimality gap on a preliminary dataset. The details can be found in the paper. For the following experiments, we used the best performing CP model called element-free sumlens.
On this slide, you can see the aggregated results on several benchmark datasets. The datasets differ in scale of the instances, namely the number of jobs, intervals, and size of the transition graph. We have re-implemented the reference ILP model from the literature, and all the ILP models were solved by Kurobe, and the CP model was solved by IBM CP Optimizer.
As you can see from the results table, our ILP model called ILP spaces solves all the benchmark instances to optimality within the given time limit. On the other hand, the reference ILP model called ILP ref solved only 23% of the benchmark instances, mainly from the medium dataset. Moreover, the average running time of the ILP ref on the solved instances is several times larger than for the ILP spaces.
Although the CP spaces did not solve any instance to optimality, on average it provides solutions with higher quality than ILP ref, which can be seen from the optimality gap column. Furthermore, it can be clearly seen from the optimality gaps that our models scale well even when larger transition graphs are considered.
Finally, let's conclude our presentation. The main contribution of our work is an efficient pre-processing technique for established problem called one-to-states tag and its integration to ILP and CP models, which were shown to be more efficient compared to the existing modeling techniques.
Our model can solve all the benchmark instances with up to 190 jobs and 1,200 intervals within an hour of computations, whereas the reference ILP model from the literature solved only 23% of the instances. This size corresponds to a 1-day scheduling with 1-minute granularity, or 1-week scheduling with 5-minute granularity, which is practically relevant.
We thank you for watching our presentation. In case of any questions, feel free to ask. Thank you very much. Bye.
Bye.